All right, so thank you everybody for joining. It looks like everybody got their data when we needed it. And so now I've started the recording. So if you want to type your name into the chat so we have your attendance, you can do that whenever you want, and we'll have a record that you're here. And I would hope that overall a few more people will join in the next few minutes as people get their data cards more. So I'll be paying attention to see if anybody's coming in. Okay, so great. So welcome everybody. Hope you all had a nice week and are ready to do a little bit more trigonometry. We're going to talk about today. Just a little heads up for what's coming up for the next couple of weeks. So we will have class next week. That's March 8th. And then there's going to be 2 weeks in a row that we don't have class. So March 15th for J.J. Roberts' birthday, there's going to be no class. And March 22nd, there's also going to be no class because I have another commitment. No, decline. What just happened there? Sorry, let's try this again. Okay, so there'll be class next week, but then there's going to be a 2-week break, and we'll resume on March 22nd. I'll send this all out on the chat, but just letting you guys know now. Okay, so last time we were talking about how to evaluate trigonometry functions at angles that are not necessarily between 0 and 90 degrees. So that means that we can't just use a right triangle to evaluate these because the angles in a right triangle are always between 0 and 90 degrees. So we had a technique for how to do it for general angles. And maybe before we even go over the homework problems, I'll just recall what we had for this technique. We had this unit circle, right? So we drew this circle that had a radius of 1. And if you want to evaluate sine and cosine at some angle, let's say 120 degrees, then you have to draw the line that lies at 120 degrees from the positive x-axis, always going counterclockwise. So 0 up to 90, to 180, to 270, and up to 360, which is the same as 0. So you go over to 120, you draw the line at the angle, and you see where that line hits the unit circle. And wherever that line hits the unit circle, the x-coordinate is the cosine. So that's cosine of 120 degrees, and the y-coordinate is the sine. So that's sine of 120 degrees. Okay. And great. So this is how we did that. And usually you're not going to necessarily draw the circle every time. So we had a method for how we're going to calculate if you need to calculate a trigonometric function of some large angle. Well, this is just recalling from last time. For any acute angle, we saw that if you have an angle theta, then these other angles, 180 degrees minus theta, 180 degrees plus theta, and 360 degrees minus theta, that they all give the same values of the trigonometric functions, except maybe you're going to get an extra plus sign or minus sign. And so with 60 degrees, for instance, we see that 60, 180 minus 60, which is 120, 180 plus 60, which is 240, and 360 minus 60, which is 300, that all of these give the same values for cosine up to maybe a plus or a minus sign. And we say here that this 60 degrees is called the reference angle for these angles, 120 degrees, 240 degrees, 300 degrees. And then how do we know plus or minus? Well, we had this method where the ASTC method, going counterclockwise. And this is where all trig functions are positive. This is where only the sine is positive. This third quadrant here is where only the tangent is positive. And this fourth quadrant here is where only the cosine is positive. Okay. And so this is just a review of what we did last time, but I also got a request last time to talk about how to find reference angles. So I'm adding an extra slide for this. So let's talk about this. This is the method. So how do we find a reference angle? So if you're given an angle that you have to find some trig function of, and you want to know what is the reference angle, so what happens? Well, if the angle that they give you is between 0 and 90 degrees, then the reference angle for theta is just theta itself. If it's between 0 and 90 degrees, you don't need a reference angle. You just use the angle as is. If it's between 90 degrees and 180 degrees, then the reference angle for theta is 180 degrees minus theta. If the angle is between 180 degrees and 270 degrees, then the reference angle for theta is theta minus 180 degrees. And lastly, if you have 270, if theta is between 270 degrees and 360 degrees, then the reference angle for theta is 360 degrees minus theta. So example, like what we had before, if theta is equal to 120 degrees, then the reference angle for theta is, well, we have to look. Well, 120 degrees is between 90 degrees and 180 degrees. That means we got to take 180 minus theta. So it's 180 degrees minus 120 degrees, and that would be equal to 60 degrees. Or another thing, if theta is, 330 degrees, then the reference angle for theta is, well, 330. That's between 270 and 360. So we have to use this formula, 360 degrees minus theta. So the reference angle for theta is 360 degrees minus 330 degrees, and that's going to be 30 degrees. Okay, so this is the method to find a reference angle, at least for angles between 0 and 360 degrees. We'll talk a little bit today about what you do when the angle is more than 360 degrees, or if it's a negative angle, which is something that you can still do sine of a negative number. So we'll talk about that today. Okay, so all right, any questions about this?
Yeah, sure. For me,
Yeah.
I got it now. I got it.
Okay, good.
Yeah.
Okay, good. All right, so now with this in mind, let's go back to the let's go back to
Yeah,
let's
I
go back
think
to the
that
question.
is clear. It's clear. Thank you.
Okay, great. Okay, so let's now go back to the homework questions. Okay, so we have homework exercise 1. Calculate tangent of 300 degrees using a reference angle from the chart. So what do we have? Okay, so we need to do reference angle. So for 300 degrees, what's the reference angle going to be?
Yeah,
Yep,
the reference angle for 300 degree will be 60 degrees.
right, exactly.
Hello?
So yes, hello?
Yeah. I just want to call you. It's 60 degrees because the angle for between 270 degrees and 360 degrees. So we subtract the 300 from the 360. So it will be 60 degrees.
Gotcha. That's right. So it's exactly right. 60 degrees, I think. So the reference angle is going to be 60 degrees. So the reference angle in this case is 360 minus 300, which is equal to 60 degrees. Okay, great. So the reference angle is 360 minus 300, which is going to be 60 degrees. And then, great. So now we need to do tan 300. So tangent of 300 degrees is going to be equal to, plus or minus tangent of 60 degrees. Now, what is it? What's it going to be? Remember, we have ASTC, the ASTC. So 300 degrees is in the fourth quadrant. So is tangent going to be positive or negative there?
tangent is negative.
Negative, exactly. So it's going to be negative of tangent 60 degrees because it's in the, because with the 300 degrees is in this fourth quadrant over here, right? It's bigger than 270. So now we just have that this is, so this is negative tangent of 60 degrees. And either you remember what tangent of 60 degrees is, or you look it up on the chart that we have over here. It says tangent of 60 degrees is square root of 3. So in this case, we have that we have minus tangent of 60 degrees, and that's going to be minus square root of 3. So that's our answer here. So maybe I'll say this here. We have to use the ASTC method.
Yeah, done.
Yes, question.
Yes, sir.
Prince? Question?
Yeah, sir. Prince.
Yes.
Yeah, I have a concept the extra parts to calculate. Yeah. I'm bringing a question. Are you getting me?
Yeah, I'm getting you.
Are you getting me, sir?
Yes, I'm getting you. Can you hear me?
I'm saying I have a concern where we have to calculate. Okay, where we have to calculate tangent of 300. Yeah, I'm hearing you.
Yeah, good. Okay, so tangent of 300 is okay?
Okay, where we have to calculate tangent of 330 degrees, but then can we use calculator to solve for tangent of 330 degrees? 300
Sure.
degrees?
Yeah, I mean, a calculator will, sure, if you have a calculator, you can use it for anything. But what you have to make sure with your calculator is that it's programmed in degrees. So most calculators that have trigonometry, you can input your angles either in degrees or in radians. And for a calculator with trigonometry, you have to make sure that you're using degrees, because if you put the input in radians, then it's not going to work.
Okay. Thank you, sir.
Okay, 1 second. All right, 3, 4, 5, 6, 7, 8, 9. Okay, great. Okay, other questions about this?
And the next thing I observe is if you're using a calculator, your answer will end in decimal.
Right. Yeah, so the answer is going to be a decimal, so you might not recognize this as exactly square root of 3, right? Sometimes if it's 1/2, you'll recognize that, but often you'll just get a decimal. But I mean, for any application, a decimal is going to be good enough, right? You'll have enough decimal places to make that work. Okay. All right, so let's move on. So second question, suppose A is sine of 40 degrees and B is cosine of 40 degrees. Calculate cotangent of 220 degrees in terms of A and B. Okay, so this is sort of multi-step. So first we're going to find the reference angle. Okay, so for 220 degrees, how do we find the reference angle?
The reference angle for 220 degrees will be 180 minus 220.
Careful, just 220 minus 180, right? Because it should be something positive. Exactly. Great. So here we have, it is, the reference angle is going to be 220 degrees minus 180 degrees. That's 40 degrees, which is lucky because that's exactly what we have. So we have that 2, we get that cotangent of 220 degrees is going to be equal to plus or minus cotangent of 40 degrees. And now with cotangent, you have to be a little careful when you use this ASTC method. This only works for sine, tangent, and cosine. So if you have cotangent or secant or cosecant, then you need to just use its inverse instead. So we know that cotangent is... Yes, Prince?
Yeah, so the tangent is positive, then the cotangent will be negative.
No. So if the tangent is positive, then the cotangent is also positive, right? Because they're reciprocals of each other. So if one is positive, then the other one's also going to be positive because they're reciprocals. One is sine over cosine, the other is cosine over sine. So what we have here is actually the tangent. We're in the third quadrant, so the tangent is positive, and that means the cotangent is also positive. So I'll just say tangent
Positive. Okay.
positive implies that cotangent is positive.
So I have a question, sir.
Yep.
Yeah, so for every inverse, it carries the sign which is given in this quadrant for every inverse. Like for instance, you
Exactly.
have sign here. Okay.
Exactly.
So
So
you get the same for
cosecant,
every
if exactly. So if sine is positive, then cosecant is also positive. That's the inverse. Yeah, the inverse never changes the sign.
Okay, okay.
Okay. So great. So it's going to be positive. So it's positive cotangent of 40. Now, I don't know what cotangent of 40 is. I could do it on a calculator. I don't know what it is. But the question just says to do it in terms of A and B. So what we have here is step 3 is that cotangent of 220 is equal to cotangent of 40 degrees. And by definition, cotangent is cosine of 40 degrees divided by sine of 40 degrees. Right? And so, well, we have that B is cosine of 40 degrees and A is sine of 40 degrees. And so this gives us B divided by A, which is the answer here. Okay, so the answer to this question is B over A. I mean, you could write it as in terms of a decimal if you wanted to, but the question asked you to just find it in terms of A and B. Okay, so that's this is what you get. Cotangent of 220 degrees is the same as cotangent of 40 degrees. And once you have that, you have to remember what cotangent is. Okay. All right, any questions? Okay. Let's do the next question, which is kind of similar. So same thing. A is sine of 40 and B is cosine of 40. Now we need to calculate cotangent of 230 degrees in terms of A and B. Okay. And then can we calculate it in terms of A only? So we have to start again the same way. Start with the reference angle. And for matter of time, I'll just do this. 230 is going to be the same as 220. We have that the reference angle is going to be 230 degrees minus 180 degrees. It's in the same quadrant. This is going to be 50 degrees. Okay? And so this means that we have that. So cotangent of 230 degrees is going to be equal to plus or minus cotangent of 50 degrees. But again, we have ASTC. We're in the third quadrant. So tangent is going to be positive, which means cotangent is positive also. So this is going to be cotangent of 50 degrees. Right. Okay, so that's good. So now, does anybody know what to do from here? So we still have to calculate in terms of sine 40 and cosine of 40. Sorry, Abraham, we're going to answer?
Yeah. Then from there, put
Sorry.
40 degrees.
Yep. Yeah, I'm not getting you very clearly. So yep. Okay.
So we say the cosine of 50 degrees is equal to
Yeah, so
40 degrees divided by 40 degrees.
Aha, right. Okay, good. So we're observing, so cotangent of 50 degrees, right, is cosine of 50 degrees divided by sine of 50 degrees. And then you're observing that cosine of 50 degrees is equal to, I think I heard you right, this is sine of 40 degrees. And also sine of 50 degrees is equal to cosine of 40 degrees. Remember, this is an identity that we proved using the right triangles, because these are the 50 and the 40 occur in the same right triangle. So by switching switching which angle you're talking about, it turns sine into cosine and cosine into sine, right? So when I have two angles that add up to 90 degrees, then cosine of one of them is the same as sine of the other one. So here we have, so cosine 50 over sine 50, well, cosine 50 is sine of 40, and sine 50 is cosine of 40, right? And so now we see that this is exactly A over B. So that's the answer here. Okay, so the reference angle gets us something in terms of 50 degrees, but actually the question is asking you in terms of sine of 40 degrees and cosine of 40 degrees. So you need to be able to convert 50 degrees to 40 degrees, but you can do that because 50 and 40 add up to 90 degrees. They're complementary angles. And that means that you can, if you know trigonometry functions at 50 degrees, you also know them at 40 degrees. You just have to switch the function. Okay. So any questions on this part of the problem? And so now the last part says, can we rewrite this in terms of A only with no B's? Okay. And the answer here, right, is that in fact, for the last part, well, we know that sine squared of 40 degrees plus cosine squared of 40 degrees is equal to 1. This is the most important identity in trigonometry, right? So this tells us that a squared plus b squared is equal to 1. And in particular, what does this tell us? This tells us that if we want to write everything in terms of a, we want to solve for b. So b squared is equal to 1 minus a squared. And that tells us that b is equal to square root of 1 minus a squared. And so normally I would have to put a plus or minus here, right? If I'm trying to solve an equation like this and I take the square root of both sides, I would have to put a plus or minus here. But actually, what is b? B is cosine of 40 degrees. This is an angle in the first quadrant. All trig functions in the first quadrant are positive. So we know that cosine of 40 degrees is positive. So B is positive. So that means we don't have to put plus or minus over here because we know that B is positive, right? There's no possibility for it to be negative because B is cosine of 40 degrees. So what this tells us then is that so cotangent of 50 degrees, which we already know is equal to A over B, this is also equal to A over square root of 1 minus A squared. Okay. So the first part of the question, the answer is A over B. The second part of the question, the answer is A over square root of 1 minus A squared. Okay. All right. Any questions on this? Okay. Great. Okay. So let's move on then. Okay, so these are the homework questions. So let's move on. And just a reminder, if you haven't yet, please remember to put your name in the chat so that we have your record for attendance. Okay, so we're gonna go past this unit circle, reference angles. Okay, so I want to talk a little bit more about trigonometric identities. So one thing that's an important takeaway that we have from this homework number 3 is we have this fundamental identity of trigonometric functions, which is that sine squared of x plus cosine squared of x equals 1 for all values of x, no matter what. Okay, this is not only true for x between 0 and 90 degrees, but it's true for any possible angle that you could put in. Okay. Boima, do you have a question? If not, I'm going to mute you. Okay. All right. So, okay. So in fact, you get another couple of identities for free. So if you take this identity and you divide both sides by sine squared of x, then you get a new identity. So what happens if I take this and I divide it by sine squared of x? I'll just write that over here. What do we have? We have that sine squared of x plus cosine squared of x is equal to 1, and I divide everything by sine squared of x. I divide everything by sine squared of x, so the identity certainly still works. So I'm dividing everything by the same quantity, and then this sine squared of x divided by sine squared of x, this is equal to 1. Cosine squared divided by sine squared is cotangent squared, and 1 divided by sine squared is cosecant squared. Okay, so what we see is if we take this identity and we divide everything by sine squared of x, we get this new identity, 1 plus cotan squared x equals cosecant squared x. And similarly over here, if we take sine squared x plus cosine squared x equals 1, and we divide everything by cosine squared x instead, then what we get is sine squared over cosine squared is tangent squared. Cosine squared over cosine squared is 1. And 1 divided by cosine squared, well, 1 divided by cosine is secant. It's the inverse. So 1 divided by cosine squared is secant squared of x. And so we get this other identity. So we have 1 plus cotangent squared equals cosecant squared, and tan squared plus 1 equals secant squared. Okay?
Yes.
So, yes, question. Princeton?
Getting this out, it seems to be like all the other identity derived from the first identity.
Right. Well, these are both derived from the first identity. There are other trig identities that you can't derive from the first identity, but these two have an easy derivation from the first identity.
Yes, hello.
Yes, Princeton?
Yes, I want to know if we can also get this identity from it. They're making sine square s to be the subject. So can we also get one identity? Because in making it, I think it would be like sine square s equal to 1 minus cos square s. Can we be having this other identity?
Sure. Yeah, I mean, you can manipulate this identity however you want, right? So if you want to write this as an identity for sine squared, you could move the cosine squared to the other side, and you'd have sine squared equals 1 minus cosine squared x. That's fine.
Okay.
Yeah, that's fine. Usually we write the identity this way because it reminds us of the Pythagorean theorem, right? Why does this identity work in the first place? Well, remember, we have our unit circle, and here we have a right triangle here. And what are the sides of this right triangle? Well, this is the unit circle, so the radius is 1, right? The hypotenuse is 1. And then the coordinates here are sine x and cosine x. So what that tells us is that the y coordinate here, which is the length of this side, is sine of x, if this angle is x. And the x coordinate, which is the length of this side, is cosine of x. And so then we get from Pythagoras' theorem that sine squared x plus cosine squared x is equal to 1 squared, which is 1, right? So this identity is really just the Pythagorean theorem in the unit circle, right? That's all that you're using. So that's the reason why, I mean, you can take any of these identities and derive all of the other ones from it, and you can rearrange them and get all sorts of different looking identities. But I think of this as really the fundamental one, because this is the one that's coming from the Pythagorean theorem. Okay, this identity works because the Pythagorean theorem works. And once you know this, then everything else comes from manipulation. But this is the one that's really saying something about geometry. Okay, it's using the Pythagorean theorem to get that sine squared plus cosine squared is equal to 1 by using a right triangle. Any further questions about these identities?
Yes,
Yes,
sir.
Prince.
Yeah, Yes, where my attention has been drawn to from where we got tangent tangent to be equal to sin theta or cos theta. So
Right.
how tangent was given as to be expressed as sin theta or cos theta? How? Because I just actually want to know.
Okay, so we did this last time, so I'll just remember that for tangent, right, we had that sine is equal to opposite over the hypotenuse, and then cosine is equal to the adjacent over the hypotenuse. And so then what happens? Then sine over cosine is equal to the opposite divided by the hypotenuse over the adjacent divided by the hypotenuse. And then you could cancel this out, right? So this is equal to opposite divided by hypotenuse times the inverse. So times hypotenuse over the adjacent. And now cancel, cancel. And what you're left with is the opposite over the adjacent, and that's exactly equal to 10. Right? So so this is the point. If you take the definition of sine from a right triangle and cosine from a right triangle and divide them by each other, you exactly get the definition of tangent from a right triangle.
Thank you. So is it applicable for us to also use a right angle triangle to identify by solving for sine, cos, and that before getting to tangents to be equal to sine or cos? Is it
Yeah,
applicable to use a right angle triangle?
yes, you can. I mean, although it's usually, if you have a right angled triangle, it's usually easier to just use the sides directly to get tangent. This sine over cosine definition is most useful when you don't have a right angled triangle and you're trying to say something about tangent. Okay, so if all you know is sine, and it's a good way to know things about tangent to derive things about tangent while only memorizing things about sine and cosine. If you have a right angled triangle, it's usually easier to just directly use opposite over adjacent in order to calculate tangent. But when you don't have a right angled triangle, this equivalent definition is sometimes more useful.
Okay. Thank you so much.
All right.
Thank you.
You're welcome. Okay. All right, let's move on. So, okay, so I want to talk about radian angle measure today, right? So in more advanced trigonometry and especially in calculus, we almost always measure angles in radians and not in degrees. Okay, it's just a different scale. It's like measuring a length in feet instead of in inches, or measuring weight in kilograms or in pounds, right? It's just a different scale, and it just has a conversion factor from radians to degrees. So what's the definition of a radian? Well, a radian is a measure of the central angle in a circle whose arc length, so this is the arc length of the angle, is the same as the radius of the circle. Okay? So here we have a circle, a central angle with theta, and if you make the angle big enough so that the amount of arc length here is exactly the same as the radius, then that angle is called 1 radian. And what we see here is 1 radian, we claim, we'll prove this, is equal to 180 over pi degrees. This is, roughly, I think, 57 degrees. Look at 180 over pi, make sure that's right. So 180, my computer's going a little slow. 180 divided by pi, yeah, it's about 57 degrees. Okay, so right. So why is 1 radian 180 over pi degrees? Well, let's look at it. We know that, for instance, so we know that if theta is equal to 180 degrees, the associated arc length, right? So what happens if theta is equal to 180 degrees? The associated arc length would be an entire 180 degree angle. So the associated arc length would be the entire top of the circle, right? So the associated arc length in this case is 1/2 of the circumference. And that's equal to 1/2 times 2 pi r, which is equal to pi times r. So what this tells you is that 180 degrees is equal to pi radians. Okay, right? Because 1 radian would be an angle that cuts out an arc length of r. So if you have an angle that cuts out an arc length of pi r, then you're getting pi radians. If it was r, it would be 1 radian. Since it's pi r, it's pi radians. So if 180 degrees is pi radians, then you can divide both sides by pi. So 180 divided by pi degrees is equal to 1 radian. Okay. So this is the conversion factor from radians to degrees, right? If you have a measure in radians and you want to multiply it by, you want to write it in degrees, you have to multiply by 180 over pi. And in reverse, if you have a measurement in degrees and you want to measure it instead in radians, you have to multiply by pi over 180. So to convert degrees to radians, multiply by pi divided by 180 degrees. Okay. Questions? Okay, so let's just work with this for a little bit. So quick exercise, how many radians is a right angle? So we can do this the easy way by just multiplying by the conversion factor, but let's try to do it instead just from first principles. I have a right angle. I have RR, this is my right angle. So what is the arc length here? So how much of the circle does a right angle cut out? Well, it cuts out a quarter of the circle, right? So the arc length in this case is equal to 1/4 of the circumference, which is equal to 1/4 times 2 pi r. And that's equal to 1/2 times 1/2 pi times the radian times the radius. And so this tells us that that a right angle, 90 degrees, is equal to 1/2 pi or pi over 2 radians. Boim, if you can keep your mic off if you're not asking a question. So yeah, so it's pi over 2 radians. Okay, so or if we wanted to use the conversion factor, or you could just say 90 degrees times our conversion factor, which we saw over here is we just multiply by pi over 180 degrees. So 90 degrees times pi over 180 degrees is equal to pi over 2 radians. So of course it's the same answer either way, but this is the kind of, geometric reasoning. And this here would be algebraic reasoning. Okay, any questions?
Me, it's okay, sir.
Yep.
It's okay
Okay.
for me. What honestly.
Good. Okay, so let's keep going. Okay, so we've seen that a right angle is pi over 2 radians. A complete circle, which would be the whole radius, is going to be 4 right angles, so that's 2 pi radians. And so when we consider the trigonometric functions, then we allow theta to be any real number. So far, we've only done inputs between 0 and 360 degrees, right? Which is the same as 0 up to 2 pi radians. That's the complete circle. But what we do when we allow any input to a trigonometric function, to sine or cosine, is that we allow theta to be any real number at all. And what we say is that when we add or subtract a multiple of 360 degrees or of 2 pi radians, then that doesn't change any of the values. So looking at the unit circle, for instance, where's our unit circle picture? Here it is. So if we did, let's say, 450 degrees, what would you do? You'd go once around for 360 degrees, and then you'd go 90 degrees more to get 450. And so what we see is for any trig function, the value at 450 degrees is the same as the value at 360 degrees. Sorry, 450 degrees is the same as the value at 90 degrees. Okay, so adding or subtracting 360 doesn't matter. And if you're working in radians where 360 is 2 pi, what we say is that adding and subtracting 2 pi doesn't matter. By the way, on this picture here, these measurements are the radian measures of the angles. So pi over 6 radians, pi over 4, pi over 3, pi over 2, etc. Okay, so all of these, all of these are radian measures, and if you add or subtract 2 pi, it makes no difference. So, because 2 pi is the same as 360 degrees. So over here, we see, for instance, that sine of 17 pi over 4, well, that's a big angle, but we can always add or subtract a multiple of 2 pi. So let's subtract 4 pi. If I take 17 pi over 4 minus 4 pi, that's 16 pi over 4. We end up with sine of pi over 4. Okay, and this sine of pi over 4, if you want to recall, you multiply by 180 over pi. Pi over 4 is going to equal to 45 degrees. Or if you don't want to do the conversion yourself, you can always look it up on this graph over here. Pi over 4 is the same thing as 45 degrees. Okay, because you multiply by 180 over pi, the pi's cancel out, and you're left with 180 over 4, which is 45. Okay. Okay, so in general, this is the general rule. So when we evaluate a trig function, we can add or subtract as many multiples of 2 pi as we need so that the argument ends up being between 0 and 2 pi. And once the argument's between 0 and 2 pi, then you can use whatever method you want to evaluate the function. You can use the unit circle, you can use reference angles, anything that you want to do. But first, you need to get the argument to the trig function between 0 and 2 pi. And this is all talked about in terms of radians, but the same thing works for degrees. Instead of adding and subtracting multiples of 2 pi, you can add or subtract multiples of 360 degrees and from the argument, and that doesn't change the value of any trig function. Okay. So it doesn't matter. Sine, cosine, tangent, cotangent, cosecant, secant. Everything is going to be the same if you add or subtract 2 pi or any multiple of 2 pi. Okay, so sine of 9 pi is the same as sine of pi, which is sine of 180 degrees, and sine of 180 degrees, if you look at the graph, is going to be 0. All right, so any questions on this? Questions? Hello. Princeton?
Yeah. So if I have the 120 degree and then I want to convert this 120 degree to pi.
Yeah.
Yeah, so what can I do?
Okay. Okay, so you can use the conversion factor, right? So if you want to use a conversion factor, what do we have over here? With degrees to radians, you multiply by pi over 180, right? So to convert degrees to radians, so if you had 120 degrees, you just multiply by pi over 180. And so that ends up reducing to 2 pi over 3.
Okay.
Is that okay?
I was out. Yeah, I was out for now, so I couldn't see this.
Oh, sorry. Yeah. So this is the conversion factor here. Yes,
Okay,
Abraham.
Thank you.
You're welcome.
So what I'm saying is, if I want to convert like 45 times 45 to radian measure,
right?
how can we do that?
So then you just do the opposite. So here we have the other conversion factor. So 180 over pi degrees is equal to 1 radian. So, so sine of 45 into radian measure. Yeah, so you just take 45 and you multiply by pi over 180, right? And so that ends up being pi over 4. If you take, for you know, the example there would be, what do I want? Okay, you need to stay muted. Okay, let me add another page just with the example. So, you know, example, you know, if I have sine of, you know, sorry, so 45 degrees, you have to multiply it by, you know, 45 degrees, you have to multiply it by pi over 180 radians is equal to 1 degree. And so the degrees cancel each other out, and you end up with 45 pi over 180 radians. And that's the same thing as pi over 4 radians. Okay, Boima, you need to keep your mic off. It keeps coming on. Please keep it off. Thank you. Pi over 4 radians. Okay, so does that answer your question?
Thank you.
Okay, you're welcome. Other questions? Okay, so what's part of the point of having sine and cosine be able to take so many different values, not just values between 0 and 90, and not even just values between 0 and 360, but that you can plug in any real number at all that you want? Well, the point is this means that we can graph them as functions, right? So we can look at a graph of y equals sine x and y equals cosine of x. And when you see this in the context of a graph, it is always, always, always assumed that x is being measured in radians, unless you say specifically otherwise that you mean degrees. So when we say y equals sine x as a function, x as a real number, we're thinking of that many radians. So if I plug in x equals pi over 2, that's 90 degrees. Sine of 90 degrees is 1. So if I think of this as pi over 2, then sine of pi over 2 is equal to 1. So that means on this graph, we will have the point pi over 2 comma 1. Okay. So there are good questions. Yeah. So there are good, so you may have a graphing calculator, and if you don't have a graphing calculator, there are good websites that do this. I think I'm not going to use the applets right now, but this desmos.com is really good. So let me show you what this, let's first look at the unit circle. So what happens to, let's say, sine of x, right? So if we look at the unit circle over here, where's the unit circle, right? So if I do sine, well, sine of 0 is 0. And remember, sine follows the y coordinates. So as my angle gets bigger, sine goes up to 1, and then back down to 0, and then down to -1, and then back up to 0, and so on, right? And then again, we keep going around up to 1, down to 0, down to -1, and back up to 0. Okay? So let's look at, you know, what that's going to look like when we see. So I'm going to use this Desmos question. Okay. Question, Boima? Okay, Boima, you keep unmuting yourself. Please don't do that. Please keep your mute on. Thank you. Okay, I need to. Can I force a mute? You need to keep your mute on. Okay, please stop unmuting. Okay. So, okay, where are we? Okay, so I want to show you this desmos.com. So let me show you this on my screen. Let me stop the share here. How do I do this? Okay, share screen. Okay, so there's this website, desmos.com, which is a good graphing calculator. So you type it in, desmos.com. Gonna load the website. So graphing calculator. is this. I mean, so it does lots and lots of things, but at its very basic, it does a graphing calculator so that you can type in an equation. So if we want to type y equals sine of x, you just type it in, and there, the graph shows up automatically, right? And what we see is it has this wave-like behavior that we saw that I showed you about in the unit circle, right? Sine of 0 is 0, and then it goes up to, it even marks some points for you. So at pi over 2, sine is equal to 1. Then it goes back down to 0 at pi, and then it goes down to -1 at 3 pi over 2, and back up to 0 at 2 pi. Sorry, question? Question? James, question? No. Okay. All right. So, great. Okay. So you can just do this. And also you can do negative, which corresponds to going clockwise, right? So you can go negative, sine goes down to -1 and then back up to 0 and up to 1 and then back down to 0 and so on. So this sine graph is called a sine wave or a sine curve. And we see because as x gets bigger and bigger, the angle just keeps going around and around the unit circle, right? So we expect this graph to repeat itself. So once we do a full rotation up to 2 pi, which is here about 6.28, then the graph is just going to repeat itself. Okay, and likewise, if we do a full rotation in the other direction down to -2 pi, then again, the graph will just keep repeating itself. So we can do this for sine of x. We can do this for cosine of x, which looks more or less the same, but it starts at 1 because cosine of 0 is equal to 1 instead of 0. But otherwise, it looks kind of the same. We'll spend a little bit more time looking at this later. You can do it for tangent of x, which is going to look a little weirder. We'll talk about why that is. Not this time. We'll talk about it next time. And you can do other things like secant of x has this strange graph. And I mean, you can do whatever you want, you know, x squared plus 5x plus 6, or x squared plus 5x, x squared minus 5x plus 6. It's pretty good at just knowing what you mean when you type in a graph. And there are various things that you can do. You can fiddle around with this. You can change your range. You can graph two functions at the same time. So you can have y equals cosine of x, and you'll get both graphs together. So this is very nice. It's easy. You just type things in and it works. So it's a good thing to remember. Just desmos.com. And if you want to get to the calculator, you can type /calculator, or you can just click, if you just go to regular desmos.com, then you can just click on graphing calculator over here. Okay, and there's lots and lots of things that you can do with Desmos. Maybe I'll spend a class at some point talking about all of the things that you can do with it, but you can do three-dimensional graphs. You can do various animations and everything like this. So there's loads of things that you can do with Desmos. It's a nice teaching tool if you have an internet connection and are able to display it. But for now, we'll just use it as a basic thing just to check the the graphs of sine and cosine. Okay, so let me stop the share and put the other share back on. So let me share my screen here. All right, great. So put the chat here. Okay, excellent. So going back where we were, okay. So we can graph sine x and cosine x using the unit circle. And if we want to, we have, y equals sine x. I'll just draw it myself by hand here, just so you have it in the notes. If this is 0, this is pi over 2, this is pi, this is 3 pi over 2, and this is 2 pi, then what we saw with sine is that it went from 0, 0. If this is 1 and this is -1, then it goes up to 1 at pi over 2, and then back down to pi, and then down to -1, and then up to 2 pi. Okay. Great. Okay, so that's the graph of sine and cosine. What are some observations we have about the two graphs? Well, let me actually draw the graphs on top of each other. sine of x and y is cosine of x. So sine of x, we saw looks kind of like this. And y equals cosine of x looks basically the same, but it starts at 0, 1, because cosine of 0 is equal to 1. Okay. And both of these are labeled 1, -1. This is also 1. This is -1 over here. So what do they what do these graphs look like relative to each other? They look very similar. Do you have an observation about how one of these graphs is related to the other one? Just anything that you can say about it.
Yeah, yeah.
Mm-hmm. Yeah. Any
Hello, John.
comments? Sure. Yeah, Prince.
Yeah. You said we should look at yeah. I was sure for the first graph. Is not actually to yellow.
Mm-hmm.
Yeah, for the first graph, it's not actually to yellow. So for the second graph, no, they are more curved to yellow. Meaning it comes to yellow in that form.
Okay.
But this one is not to yellow. The first one is not actually to yellow.
So I don't
There are
understand
more
what you mean
space.
by
The first one
together.
has more space. But the second
Oh.
one has lesser space.
Okay, well, I mean, that's just how I drew them. But in terms of the, yeah, so I didn't draw these that precisely.
Good.
But, right, so, well, so they look very similar, right? There's not that much that's different about them, right?
Yeah, yeah.
Yeah, so there's not that much that's
Yes.
different. Yes, hello?
Hello.
Hello, yeah,
Yeah, for me,
Princeton?
I look at the cosine graph.
Yep,
The graph is on everything. The point are on the coordinate.
yep. So meaning up here,
Yeah.
this point.
Yeah, yes.
Yeah, right. So the cosine graph starts at 1 and the sine graph starts at 0. But it turns out, so actually, let's do this because we're almost out of time. So actually, the cosine graph is just a shift of the sine graph. Okay, and maybe I'll open Desmos one more time just to show this. So let me just open Desmos one more time. Let me see this. So if I do this, okay, so if I open Desmos one more time and I do the graphing calculator, I'm going to graph them both together, right? So if I have y equals sine of x and y equals cosine of x, so what you see, it's a little clearer here because the graphs are drawn more precisely, that you have the red curve, which is sine, it's marked in red, and the blue curve, which is cosine, it's marked in blue. And you really see that they're exactly the same, except that one is shifted over. If you shifted the blue cosine graph over a little bit, in fact, the amount that you'd have to shift it over is exactly pi over 2. That's the distance from here to here. If you shifted it over by pi over 2, then the graphs would totally coincide. Okay, so they have a lot in common. They're both periodic. They're both bounded in the y direction. You know, these functions don't take values bigger than 1 or lower than -1. But one is a shift, and these shifts make some difference. So for instance, this cosine is what's called an even function. It has reflective symmetry over the y-axis here, whereas sine of x is an odd function. It doesn't have symmetry over the y-axis. It actually has rotational symmetry around the origin. So if you go out toward the positive, for sine, it's the opposite of what happens when you go back toward the negative. So you can look at these graphs together and try to think about, you know, what properties one has that the other doesn't have, or that the other has that the one does have. But I'm just going to, for the last slide, I'm just going to write a few of the most important ones. And these correspond to other identities that we're going to have for trigonometry. And we'll talk maybe next time a little bit more about how we prove these. So let me stop my share over here. I'm going to go bring this back up. Okay, so what are some important aspects of these graphs? So just some observations. So the first one is that both of these functions are what are called periodic with period 2 pi. This is what we said on the previous slide, right? Periodic just means that if you add 2 pi to x, then it doesn't change anything. So that means that these graphs have to repeat each other every 2 pi. They go through a cycle. You go through 2 pi, it's just going to start the cycle again. So I mentioned we saw this on the graphs. Cosine x is an even function. That means that cosine of minus x equals cosine of x. Another way to think about this is that it has reflective symmetry over the y-axis. Okay. Sine of x is an odd function, meaning sine of minus x is always equal to negative sine of x. Another way of seeing this, I don't have space to write it there, but I'll say that this has rotational symmetry about the origin. So rotational symmetry of 180 degrees about the origin, meaning if you give it a half spin around the origin, the graph just comes back to itself. And then the other observation is that the graph of y equals sine of x comes from moving the graph y equals cosine of x pi over 2 to the right, right? This is what I pointed out when we were looking at the graph, right? And so what does it mean? If you can move the graph of cosine of x pi over 2 to the right and get the graph of sine of x, that means that if you take something, if you want to know what cosine of an angle is, well, cosine of x, what is it? Well, whatever that is, if you moved it pi over 2 to the right, it would be sine of x. So if you add pi over 2 to x and then apply sine, that's going to be the same thing as what you get when you have cosine. And this works in reverse also. So you get that sine of x in this case is equal to cosine of x minus pi over 2. So we're going to see later is these are special cases of what's called the so-called addition formula. Addition formulae. Okay, so we'll see these addition formulae probably not next time, but the class after that. And then there's some other identities that you can see with these graphs. If you graph them on Desmos or on a graphing calculator, you'll see that if you add pi to x, it doesn't necessarily give you the same result. If you add 2 pi, you get sine of x plus 2 pi equals sine of x. But sine of x plus pi is going to be minus sine of x. And likewise, cosine of x plus pi is equal to minus cosine of x. So on either of these graphs, if you move forward by pi, so like if I look at this graph over here, if I start here and then I move forward by pi, I get exactly to its negative. And ditto here. If I start here and I move forward by pi, turns out that's going to get me exactly to the negative. So this y value will get me to its negative y value. So for cosine and sine x, we have these identities. We're going to show these as specific cases of much more general identities. Yes, Clinton, a question?
Yeah. Observation.
Yep.
Observation. Yeah, and observation under the fourth point.
Yes.
For the identity. Yeah, under the observation there, the fourth point for the identity for sine of x.
Yep.
I'm seeing a negative for sine x equal to cos of. You don't think it should be x plus pi over 2?
So this identity sine x equals cosine of x minus pi over 2?
Yeah.
No, I think this is right. Like let's look at an example, right? So sine of I don't know 120 degrees is equal to, well, we know that sine of that's the same as sine of 60 degrees using reference angles, and that's square root of 3 over 2. Now let's look at the identity. What would we get? We get cosine of 120 degrees minus pi over 2, which is 90 degrees. And that's equal to cosine of 30 degrees. And that's also square root of 3 over 2. So it's not a proof, but it's a check. So yeah, I think this identity is correct. Yeah. And the point is that how do I evaluate sine of x? Well, if I know that cosine of x is pi over 2 to the right of sine of x, then if I want to do sine of x, I can do cosine of x, but I've got to move pi over 2 back to the left before I evaluate sine of x. That's why I have x minus pi over 2 here. And then that will give me that. Right, we also have this identity that sine of x equals cosine of pi over 2 minus x. We know that from the right triangles, but this is just another way of writing the same identity. That's
Okay,
a
yeah,
little bit
sure.
more clear from the graph. Okay.
Sure.
All right, great. Okay, so that's it for today. We're going to talk a little bit more about graphs and identities next time, and we'll be able to go a little bit slower. So there is some homework. So first question, just very straightforward. How many radians is 510 degrees? Second one, a little trickier. Suppose that a circle has radius 3, and we want a central angle that cuts out a sector of area 3 pi over 2. So if I have a circle with radius 3, and I take some sector so that this area is 3 pi over 2, right? So the question is, what is the angle? So you have to do a few steps in order to get this. The question is, what is the angle there? And in radians, we want to know what's the angle in radians. And then 3 is also a little bit easier, just to simplify the expression sine of x plus 5 pi so that it involves only sine of x. So what is the relation of this expression to sine of x? Okay, so I'll post this on the chat as always. And so thank you again for your attention. And next week on March 8th, we will discuss radian measure and, oh, sorry, I didn't update this from last time. We're not going to do this. Next, on March 8th, we will discuss graphs of trigonometry functions in more detail. Graphs of trig functions in more detail. And more trig identities. And then, so that is March 8th, that's next week. And then just for the people who weren't in at the beginning, so we want to note that there's going to be 2 weeks with no class. So March 15th, no class for the holiday. We'll have no class on the 15th. And then March 22nd, there's also no class. This is because I'm away. And then March 29th, class resumes. Okay, so we do have class on March 8th, and then no class March 15th, and no class on March 22nd, and then we resume on the 29th. Okay. All right, so thank you very much, as always, for your attention, and have a great weekend. I'll stop the recording.